This is the introduction exercise 10.2 on discrete probability distributions. We're focusing on discrete and continuous. For this component, it's just discrete. Okay, so a couple of definitions that we need to know before we get started. The first thing is that a discrete random variable, right, is one that takes place only on a countable number of values. So for example, the number of a family member or shoe size. Now there is, or you would have done this prior, do you remember your numerical and your categorical data, etc.? We're focusing just on the numerical aspect. We've got discrete and continuous. There is a very slight misconception, that is to say that discrete must be whole numbers. That is not necessarily correct, right? We teach that in junior years because it makes more sense, right? But technically, for example, shoe size, which can be 8.5, you can have an 8.5, right? That is still discrete. So it's a countable number of values, right? Because you can have 6, 6.5, 7, 7.5, etc. Right? But you can't have 6.3782, right? So it's discrete. A continuous random variable, which we're not focusing on today, is one that can take any value in an interval on a number line. So for example, your height or your weight. So that is pretty straightforward, just some key definitions for you there. We're going to focus on this aspect here, and I'd really like you to either highlight it or do something of the sort to make it very clear. These two notes here. For any discrete probability function, the two conditions must hold true. It does not matter what the variables are, etc. This must be true. Okay? The first point is that each value of p of x belongs to the interval 0 to 1. So in other words, every probability that you have must be between 0 and 1. That makes sense. Right? You can't have a probability of something being more than 1. The second one says that the sum of all the values of p of x must be 1. Really what we're doing is just saying what is our basic probability rules and writing that into function notation. The sum of, and this x you will commonly see rewritten this aspect here rewritten as this, where the x is on the bottom. Oh my gosh, let's try that again. There we go. Where the x is written on the bottom. Just means the sum of all x values in your p of x must be 1. Right? And that'll come in handy when you're solving those exam questions later, where it asks you to solve, for example, p. Right? Similar idea, but we'll get to that later on. I'm going through this quite quickly, but any questions so far? Okay. The random variable x represents the number of chocolate chips in a certain brand of biscuit and is known to have the following probability distribution. Again, it's fair to say that it's a discrete because you can't have you probably could have 3.26, but we're going to assume 2, 3, 4, etc. When we're looking at this table, the x tells us what we're looking for, right? Essentially looking at the context of the question. In this case, it's the number of chocolate chips. So x equal 2, of course, means there are 2 chocolate chips. The p of x underneath means the probability of x occurring. So of course, that's 0.01 or 1% chance to have 2 chocolate chips. That's how you read that table. Okay, so let's go through how to answer these questions. It's applying the same rules that you already know. Okay, so the first one here says that the probability of x is greater than or equal to 4. Of course, all I'm doing is identifying the values where x is greater than or equal to 4. We use capital X when we're doing these this solving aspect, the random variable x. So of course that would equal to 0.4 plus 0.3. I'm excluding the extra 0. Plus 0.2. That's 0.02 plus 0.02, which gets us 0.74. So the probability that you have 4 or more chocolate chips is 0.74 or 74%. Second question says, find the probability that x is greater than or equal to 4, given that x is greater than 2. Right? So we're still applying our conditional probability formula, where that would equal to the probability of x being greater than or equal to 4 intersecting with x being greater than 2, which it looks gross, it will look a lot simpler soon, divided by the probability of x being greater than 2. We can redefine this. We know that the probability of x being greater than 4 and the probability of x being greater than 2 overlaps. In fact, they overlap in the sense that that would equal to the probability that x, because x greater than or equal to 4 would be this section here. X being greater than 2 would be this section here. Yeah? So the overlap is just going to be the probability where x is greater than or equal to 4. That's the overlap because it's intersect. Divided by the probability, of course, we're going to keep this the same for now, where x is greater than 2. We know from the previous question that's got to be 0.74 on top. And of course on the bottom, probability that x is greater than 2. Probability that x is greater than 2 is going to be everything except it being 2. Right? And something I'd like to do before I do that is just to double check that the values do add up to 1. So those here, this is 0.7, that'll be 0.95, and add the other 3 would be 1. Good. So I can just go 1 minus 0.01, because that would be everything but x equals to 2. Right? The reason I added them up, just to double check that they're not really like neglecting any information, right? Just to make sure they've got all the probabilities there and the possibilities there as well. That would simplify to 74 over 99. Okay. Why is the probability not just, well, it says probability that x is greater than or equal to 4, right, which we know is 0.74. Why is it not just 74%? Why is the answer not just 0.74? Well, it is over 99, but why is it over 99 instead of over 100? Because it's given that. So it needs to be assuming that x is greater than 2. So that will change your probability as well. Okay? Just keep in mind you should be always use your conditional probability formula where applicable. Probability that x is less than 5, given that its x is greater than 2. If we write that out using a conditional probability, probability that x is less than 5, don't know why it's highlighting everything, intersecting with x is greater than 2, over probability that x is greater than 2. Let's go through our, well, which sections we're focusing on. X is less than 5 would be this section here. X is greater than 2 will be this section here. Oops, sorry. This section here. Right. So in other words, we can rewrite this as the probability that 2 is less than x, which is less than 5, over the probability of x being greater than 2. In other words, you could just say 3 to 4. That would apply here as well. That would equal to, because the probability of 2 being less than x being less than 5 is just going to be 0.25 plus 0.4 is 0.65 over the 0.99 from earlier, which would give us an answer of 65 over 99. Again, this is stuff that you are probably most familiar with already. The only other aspect that I'd like to focus on is this section here, where it's not something that you see very commonly. Right? It's draw the graph of a probability distribution of x. The reason why I'm doing this is because I want you to understand that these are individual values, right? It's discrete, so there should be no line connecting the points. I'm going to go ahead and graph it. I'll show you what it looks like. Again, this is not a question that will come up very often, but I'll show you what it looks like, and then we're going to compare that to a continuous graph later down the line. I'm just going based off the information in the table, but I am just copying from my notes, so that I have to keep flicking back. Please forgive the awkward silence. Okay. Yes.
You have to do the dotted line whenever you use
Yeah. Yep, you do need to do the dotted lines. You've got to label the axes. This would be P of x. This would just be x. Okay. When you do a discrete probability distribution, you'll see it visualized like this. Now, automatically, your brain will probably try to think of doing this. Right? Don't draw that line in, by the way. Your brain will automatically think of trying to do that. Do not do that. That implies a continuous. Later on in this topic, we'll do our continuous distribution. When we do a continuous distribution, it's always about the interval, not individual values. In this case, when we do the dotted line, it's symbolizing that this is just that value. The probability of 3, and again, this is something that will come into play and link back to something that you've learned earlier, is the area under the graph. It's a bit weird, but that dotted line being 0.25 is what we're focusing on. Later on, we'll do the area under the graph again, but it's over an interval. And that's when you have that curved line, you'll find the area under the graph under that curved line. Okay? But in this scenario, we're just focusing on individual points, so it's a discrete value, and that's all we're doing. Okay? Everything else is the same. Any questions? Okay.